Hello student, I am Nirmala Morade, Assistant Professor, Department of Mathematics from S.V.K.T College, Devali Camp, Nasik. In today's video, we will cover the topic Congruence and Theory of Congruence from the unit Primes and Theory of Congruence. In last lecture, we have studied fundamental theorem of arithmetic. The fundamental theorem of arithmetic says that every integer n greater than 1 can be written as a product, either it is a prime or can be written as a product of primes. Also we have studied canonical form. It is a corollary of fundamental theorem of arithmetic. So that corollary states that every integer n greater than 1 can be written as product of primes uniquely in canonical form. That is, if n is an integer, then it can be written as n equals to p1 raised to k1, p2 raised to k2, p3 raised to k3 up to pr raised to kr. Here each ki is a positive integer and each pi is a prime number. All these are the different primes and we write these primes in increasing order, that is p1 is less than p2 is less than p3 and so on. So let us consider the example 2. 2 is itself prime, so 2 can be written as 2 raised to 1. So if I take the another example as 18, so how we write this 18 as 2 into 6, again factorize 6, so we get 2 into 3. So this 18 can be written as 2 raised to 2 into 3. So this is called the canonical form of the 18. Also we have studied a famous result, that is Pythagoras result, and in this Pythagoras result we have proved root 2, the number root 2 is an irrational number. We proved this result by using the fundamental theorem of arithmetic. Now in today's lecture we are going to study congruence modulo n, that is theory of congruence, its basic properties and a complete set of residues, and also we will study one theorem or one results which is related to the theory of congruence. So after watching this video, students are able to understand the concept of congruence modulo n. Also students are able to state and apply the elementary properties of congruence. All these properties are very useful while solving the problems, and also students are able to write the relation between the congruence between the two integers and the residue of the two integers in the division by b. So let us first see what is the theory of congruence. Now this is a portrait of Gauss, German mathematician Gauss. Now this theory introduced by the Gauss. So the Gauss wrote a book. The name of the book is Disquisitiones Arithmeticae. He wrote the book when he was only 20 years old, and the book appeared, or this work appeared in 1801 when he was 24 years old. This book laid the foundation of modern number theory. So let us see the definition of congruence modulo n. So for that we required a fixed integer n, and we consider two integers say a and b. So these two integers are said to be congruent to each other modulo n if n divides the difference a minus b, that is a minus b is same as integral multiple of n, that is a minus b can be written as k times n, where k is some integer. So when a is congruent to b modulo n, then this is the notation. A is congruent to B modulo N. We use this notation to represent A is congruent to B modulo N. So now this is one example. 9 is congruent to 0 modulo N because 9 divides the difference of these two integers 9 and 0. Difference of 9 and 0 is 9 minus 0 is 9. 9 is divisible by itself. So 9 is congruent to 9. 9 is congruent to 0 modulo 9. Now let us consider the another example. 3 is congruent to 24 modulo 7 because first take the difference 3 minus 24 which is minus 21, and minus 21 can be written as the multiple, integral multiple of 7, and that's why we say here 3 is congruent to 24 modulo 7. This is another example. Minus 8 is congruent to minus 8 modulo 3. So again the reason is same here. Difference of these two integers minus 8 is 0, and 0 is divisible by any integer. So 0 is divisible by 3 also, and that's why minus 8 is congruent to minus 8 modulo 3. So now in case of if I say that A is congruent to B modulo N, then N divides the difference A minus B, or the difference A minus B is equals to K times N, where K is some integer. But if N doesn't divides A minus B, in that case we say that A is not congruent to B modulo N, or A is incongruent to B modulo N. And this is one example. 25 is not congruent to 12 modulo 7 because if you take the difference of these two, 25 minus 12 is say 13, and 13 is not divisible by 7. So this is a notation if A is not congruent to B modulo N. So we write this in this form. So now after the definition of congruence, let us study some properties or the basic elementary properties of the congruence. So now for that we consider n is any integer greater than 1, which is a fixed one here, and consider the 4 integers a, b, c, d. So we consider here first property. Every integer a is congruent to itself modulo n. So suppose we want to prove that a is congruent to a modulo n, then in that case we want to show that a minus a is integral multiple of n. That is, a minus a can be written as some integer into n. So we consider the difference first, a minus a, which is 0 here, and 0 can be written as 0 into n, and therefore by definition of congruence a is congruent to itself modulo n. Now let us consider the second property. The second property is if a is congruent to b modulo n, then b is congruent to a modulo n. So now we want to prove here the if then statement. So the statement between if and then is the hypothesis, and the next statement we have to prove. So here hypothesis, that is the given thing is a is congruent to b modulo n. This is a hypothesis. Now use the definition of congruence. So because of definition, a minus b can be written as n times some k. So we want to prove that b is congruent to a modulo n, that is we want to show that b minus a is the integral multiple of n. So if you observe the equation a minus b is equals to nk, so just multiply this equation by minus 1. So we get here b minus a is equals to minus k times n, that is b minus a is the integral multiple of n, and that's why b is congruent to a modulo n here. So by taking b is congruent to a is congruent to b modulo n, we get here B is congruent to A modulo N also. Now let us consider the third property. So this is the third property. If A is congruent to B modulo N, B is congruent to C modulo N, then A is congruent to C modulo N. This property just like the transitive property. So now first we have to write the hypothesis. Here hypothesis is A is congruent to B and B is congruent to C modulo N, and then use the definition of congruence. So by definition, A minus B is equals to N into some integer and B minus C is equals to N into some integer. So we consider here first integer as a K and second as a H. So now since we want to prove that A is congruent to C modulo N here, take the difference or prove the difference A minus C is integral multiple of N. If you observe these two equations simultaneously, observe both the equations simultaneously, so adding these two equations we will get our required number. So just add these two equations, so we get here A minus B plus B minus C is same as K times N into H plus K times H times N here. So here BB gets cancelled, and after cancelling this B we get here A minus C equals to N times K plus H. So K is also integer, H is also integer, so their addition is integer. So we get here A minus C equals to some integer into N. So according to the definition of congruence, A is congruent to C modulo N. So this property says that if first number is congruent to second mod N, second number is congruent to third mod N, then first number is congruent to the third number modulo N. So now let us consider the next property, the fourth one. So this is our fourth property. A is congruent to B modulo N, C is congruent to D modulo N, then A plus C is congruent to B plus D and AC is congruent to BD modulo N. Now if you observe this property is similar as an equation. That is, if we consider A is congruent to B and C is congruent to D as a first and second equation respectively, if we add them, we will get here A plus C is congruent to B plus D, and if we multiply them, we get AC is congruent to BD modulo N. Now proof is very simple here. Again we write hypothesis first and then use the definition of congruence. So in hypothesis, these are our two statements. A congruent to B modulo N, C is congruent to D modulo N. Then use the definition of congruence. So we get A minus B equals to some integer K into N and C minus D equals to H into, that is some integer H into N. So since we want to prove that A plus C is congruent to B plus D, that is we require the difference of these two integers. So if you observe carefully, adding these two, we get here A minus B plus C minus D equals to K times N plus H times N here. So if you just do the rearrangement of the terms, we take A and C combine and then B and D combine. So this can be written as A plus C minus in bracket B plus D is same as, take N as a common, K plus H times N. So the difference is multiple of N implies A plus C is congruent to B plus D modulo N. So now let us prove the next property, AC is congruent to BD modulo N. So now for that, first from these two equations, A minus B equals to Kn, find the value of A which is B plus Kn, and from the second equation, that is C minus D equals to Hn. Now write C in terms of D, so C equals to D plus Hn, okay, and then we consider the multiplication A into C. So consider the multiplication a into c, put the value of a as a b plus kn and value of c as a d plus hn. Now just simplify this bracket. So after simplifying, we get here AC equals to BD plus B times HN plus DKN plus KHNN. All these are in multiplication. Remember here A, B, C, D, K and H, all these are integers and we write in the multiplication. So now take BD in the other side. So it gives AC minus BD equals to this one, N times BH plus DK plus KHN. We take N also common here. Okay. So the difference is the multiple of N, because the second bracket BH plus DK plus KHN, this is a whole integer because B, H, D, N, all these are the integer, and as we know that the multiplication, subtraction and addition of integer is again an integer, and that's why here AC minus BD is a integral multiple of N, and so by definition of congruence, AC is congruent to BD modulo N. So it proves the result. So now our this is our last property. In last property we want to prove that A is congruent to B modulo N. Then AC is congruent to BC modulo N, as well as A plus C is congruent to B plus C modulo N. Now this property is again just like an equation. Suppose we have to given one equation. So we know that if you add any number on the both sides of the equation, then equality remains the same, or if you multiply that equation, both sides of the equation by the same number, then also equality remains the same. Same thing for this property. We have to given one congruence relation, A is congruent to B modulo N. A is congruent to B modulo N, and if you add C both the sides, then congruence remains the same. That is A plus C is congruent to B plus C modulo N, and here we multiply C by both sides. That is AC is congruent to BC modulo N. So now let us prove this property. The technique is again the same one. First write the hypothesis. The hypothesis contains only one statement here. A is congruent to B modulo N. So by definition, the difference A minus B is equals to K times N, where K is some integer here. So now first we take the difference of these two, A plus C minus B plus C. If we take the difference, then open the bracket here, CC gets cancelled here, so A minus B is remaining. And by above hypothesis, A minus B can be written as K times N. So the difference is K times N. So by definition of congruence, A plus C is congruent to B plus C modulo N. So it proves the first result. Proved the first result. Concentrate on the second result, and for that again we consider the difference AC minus BC. So by taking the difference AC minus BC and take C as a common here. So if C is a common, the remaining is A minus B. Now put the value of A minus B from the above equation. So it is K times N into multiply by C. So AC minus BC can be written as KC times N. K is an integer, C is an integer, that's why K into C is a whole integer. So this difference AC minus BC is integral multiple of N, and that's why by definition AC is congruent to BC modulo N. So now let us consider the last 6th property of the congruence, and that is also very useful property. So in this property we will prove if A is congruent to B modulo N, then A raised to K is congruent to B raised to K modulo N for any positive integer K. Suppose we consider here K equals to 2, then A square is congruent to B square. Suppose I consider here K equals to 3, then A raised to 3 is congruent to B raised to 3 modulo N. In short, A is congruent to B modulo N, then any integral power of a is congruent to the same integral power of b modulo n. So, but we consider that power should be a positive integer. So, to prove this one, first we use here the mathematical induction. So, we want to prove the statement a raised to k is congruent to b raised to k modulo n by using the mathematical statement. So, let us consider or let us prove the result for n for k equals to 1. So, if you put k equals to 1, the statement becomes a is congruent to b modulo n, and which is already proved because of given thing. We have to given a is congruent to b modulo n. So, this statement is true obviously for k equals to 1. So, now use the second step, that is induction hypothesis. Assume that the same result is true for some integer m, that is a raised to m is congruent to b raised to m modulo n here. This is our induction hypothesis. So, now our next step is we want to prove the result for the next integer, that is m plus 1. So, now here just observe the first equation is congruence equation is a is congruent to b modulo n, and this latest equation is a raised to m congruent to b raised to m modulo n. Now, if you multiply both equation by using the previous property, already we have to study one property, a is congruent to b modulo n, c is congruent to d modulo n. Then we can multiply these two congruence equation, that is ac is congruent to bd modulo n. So, use that property here. So, first hypothesis is a is congruent to b modulo n, and this is a induction hypothesis, a raised to m is congruent to b raised to modulo n. If you multiply these two, we will get here a raised to m plus 1 is congruent to b raised to m plus 1 modulo n. Okay, by mistake I have written here equal sign. So, be correct there, it should be triple line. So, the statement is true for m plus 1. So, by induction hypothesis, the original statement or the given statement is true for any positive integer k. That is, if a is congruent to b modulo n, then a raised to k is congruent to b raised to modulo n for every positive integer n here. So, these are the 6 properties, basic properties of the congruence. So, remember all these properties. While solving the examples, these properties are very useful for us. So, now our next concept is the complete set of residues. So, for that we consider the two integers a and b. So, first we have to apply the division algorithm to the integer a and n. A is any integer and n is here any fixed positive integer. So, now by division algorithm or in the division of a by n, a can be written as n times q plus r with 0 is less than equal r is less than n. That is, we apply the division algorithm to a and n. So, by division algorithm there exists unique integers q and r. Q is called quotient, r is called remainder, such that a is equals to nq plus r with 0 is less than equal r is less than n. Here n is a integer greater than 1 here. So, now here a minus r can be written as n times q. So, this difference is multiple of n. This difference is multiple of n. And so, by definition of congruence, a is congruent to r modulo n. But we know that 0 is less than equal r is less than n. So, there are only n possible values of r, and that values are 0, 1, 2 up to n minus 1. So, here the integer a is congruent to r modulo n for some unique value of r either from 0 to n minus 1. So, from this we can say that every integer a is congruent to one of the integer 0 to n minus 1 modulo 1. This is our result. So, in this case, this set of n integers 0, 1, 2, n minus 1. This set is called as the set of least non-negative residues modulo n. This is called as the set of least non-negative residues modulo n. So next our concept is the complete set of residues. So here we will see which set is called as the complete set of residues. So now for that I consider here n integers a1, a2 up to an. This set is said to be a complete set of residues or a complete system of residues modulo n if every integer is congruent to modulo n. Every integer is congruent to modulo n to exactly one of the integer ak. Exactly one of the integer ak. That is, in short, a1, a2, an is congruent to 0, 1, 2 up to n minus 1, one of these, exactly one of these integer modulo n. So let us see one example. We consider here three integers minus 12, minus 5 and 8. So we want to show that this set is complete set of residues modulo 3. So we want to show that it is a complete set of residue modulo 3. That is, we want to show that minus 12 is congruent to minus 12, minus 5 and 8. These are congruent to one of the integer, exactly one of the integer 0, 1, 2. Okay. So minus 12 is congruent to 0. Why? Because if we consider the difference, minus 12 minus 0 is minus 12, which is divisible by 3, and that's why minus 12 is congruent to 0. Next one is minus 5 is congruent to 1. Again the same reason here, difference is divisible by 3, and last one is 8 is congruent to 2 modulo 3. So this set is called the complete set of residues modulo 3. So now let us study one theorem related to this congruence. So see the statement of the theorem. So for every integer a and b, a is congruent to b modulo n if and only if a and b leave the same remainder when divided by n. This is the statement of the theorem. For any arbitrary integer a and b, a is congruent to b modulo n if and only if a and b leave the same non-negative remainder when divided by n. So we want to prove this theorem. So in this case, we prove this theorem in two parts. First one is the necessary and sufficient condition. Now in first part, let us assume that a is congruent to b modulo n and prove that a and b leave the same remainder, non-negative remainder. Obviously remainder is same non-negative remainder when divided by n. And in second part, assume that a and b leave the same non-negative remainder when divided by n and prove that a is congruent to b modulo n here. So let us consider the first part. So write the hypothesis here. So our hypothesis is a is congruent to b modulo n. We assume this one, and so by definition of congruence, the difference a minus b is same as some integer into n. We write here integer k. So our aim is to prove that a and b leave the same non-negative remainder when divided by n. So now let us first consider, or we consider the division of b by n and apply the division algorithm theorem. And so there exists the quotient and remainder when we divide b by n. So there exists quotient say q and remainder say r when we divide b by n. So b can be written as qn plus r with 0 is less than r is less than n here. So now put the value of this b in above equation. So a minus b becomes here a minus, okay, first we have to write either shift in this side or we directly put also A equals to B plus Kn by above equation, and then put the value of B here. B is equals to Qn plus R plus Kn here. So combine the first and the last term. So A can be written as take n as a common. So Q plus K times n plus R. So A minus R is so here just observe here A can be written as some quotient term Q plus K into n plus R. So A leave the same remainder, or A has the same remainder as a B. So by assuming A is congruent to B modulo n, we get here A and B have the same remainder when divided by n. So in second part, this is our assumption. A and B leave the same remainder, non-negative remainder when divided by n, and we want to prove that A is congruent to B modulo n. That is, we want to prove that A minus B is equals to n times some integer. So for that, first we consider the hypothesis statement, that is A and B leave the same remainder when divided by n. So apply the division algorithm to An as well as the Bn. So there exists some quotient and remainder. So this A and B can be written in this form. Suppose the quotient for A is Q1, remainder is R, and for B quotient is Q2 and remainder is same as R. So A can be written as Q1 n plus R and B can be written as Q2 n plus R, with 0 is less than R is less than n here. Okay, this is because of division algorithm. So now take the difference of this, because we want to prove that A is congruent to B modulo n. So take the difference of these two integers. So we get here A minus B, RR gets cancelled here, RR gets cancelled, and take n common from the left side. So Q1 minus Q2 times n here. So consider here A minus B, see here A minus B is equals to some integer into n, because Q1 is integer, Q2 is integer, so their difference is also integer, and A minus B is integral multiple of n, that's why A is congruent to B modulo n here, and which proved the result here. So the statement of the theorem is, if A is congruent to B modulo n, if and only if A and B leave the same non-negative remainder when divided by n. So let us summarize our today's lecture. So at the starting of the lecture, we have studied the definition of congruence. So A is congruent, here in the definition of congruence we consider n is an integer greater than 1, which is a fixed one, and consider A and B are any two integers. So the integer A is said to be congruent to B modulo n if and only if n divides A minus B, that is the difference A minus B is the integral multiple of n, that is A minus B can be written as K times n here. So remember, this is a basic definition of congruence. After that we have studied the basic elementary properties of congruence, and these properties are very easy to remember. These properties are just like just similar as a reflexive relation, symmetric relation, transitive relation, and some properties are just like equations also. So let us recall all these properties again. So the first property is A is congruent to A modulo n. Second property is, if A is congruent to B modulo n, then B is congruent to A modulo n. This is our second property. And the third property is, if A is congruent to B modulo n and B is congruent to C modulo n, then A is congruent to C modulo n here. Now the fourth one property is, if A is congruent to B modulo n, C is congruent to D modulo n, then we can add these two equations and we can multiply these equations similar as a regular equations. So A plus C is congruent to B plus D modulo n, and A into C is congruent to B into D modulo n. So these are very easy to remember also. Now our next fifth property is, If A is congruent to B modulo n, then we add C both sides. So A plus C is congruent to B plus C modulo n, and multiply C to the both sides. So AC is congruent to BD modulo n. And our last property for the congruence is A is congruent to B modulo n, then A raised to k is congruent to B raised to k modulo n for any positive integer k. Also, we have to study the concept of complete set of residues. So, the n integers is called the complete set of residue if these n integers are congruent to n to one of the integers 0, 1, 2 up to n minus 1 taken in some order. That is sum of the integer. Suppose a1 is congruent to 2 modulo n, then a2 is congruent to 1 and so on. And we have studied the last theorem which gives the relation between the congruence of AB and their remainder when we divide by n. So, this theorem says that for any integer a and b, if a is congruent to b modulo n, if and only if a and b leave the same non-negative remainder when divided by n. So, this is a summary of our today's lecture. Actually, this topic is very easy to study. It is very useful in mathematics also. So, this is some assignment for you. So, first do the each and every topic or definition of congruence theory, its properties carefully, and then solve this problem. This is an additional reference for your study, Elementary Number Theory 7th edition by David Burton. This topic is included in chapter 4 and section 4.2. Also in the exercise, more examples related to the topic are available. So try to solve that examples. So in next lecture, we will study some more theorems and results related to the congruence. That may be include related to the GCD of two integers and the examples using definition of congruence, basic properties of the congruence as well as the theorem of the congruence. Thank you.